This project uses machine learning to increase revenue for online booking platforms like Expedia or Kayak. It predicts which customers are likely to keep buying after a price increase, calculates the probability of continuation, and dynamically adjusts prices for those who are less price sensitive, helping managers raise prices without losing sales. The system combines a FastAPI-based prediction model, a Streamlit dashboard for user interaction, and a Flask backend simulation, demonstrating how real-time ML pipelines operate in e-commerce and travel platforms. We trained the model on a dataset of 500 customers using 10 behavioral and transaction features to predict price tolerance. Let's take a quick look at those features. Total spend and average order value reflect spending habits. Higher values often signal loyalty and lower price sensitivity. Purchase frequency and days since last purchase show engagement. Frequent, recent buyers are more likely to return. Loyalty program members tend to have higher switching costs, so they're more likely to accept a price increase. Days in advance reflects urgency. Late bookers are often less price sensitive. MIME type and cabin class are product attributes. Business class and international flights typically show lower elasticity. Finally, our target variable indicates if the customer will buy again after the price increase. That's what our model learns to predict. We use logistic regression for better explainability and speed.
Here's how the model performed on the 100 test customers. We correctly classified most buyers and non-buyers, with only 9 false positives and 9 false negatives. That's what you see in the confusion matrix. The ROC curve shows an AUC of 0.91, which means the model is very good at distinguishing between customers who will continue buying after a price increase and those who won't. This performance suggests the model is reliable for real-time price sensitivity prediction. All project files are publicly available on GitHub. The README includes links to the deployed API on both Hugging Face and Render, the Streamlit app, and an integration test that confirms the API remains live and functional after any code updates. To test the API, we simply open the link, enter example customer data, and view the prediction and probability. A prediction of 1 means the customer is likely to buy after a price increase, while 0 means they're not. The probability is computed using the sigmoid function from Logistic regression. Now let's explore the Streamlit app. This tool assesses which customers are likely to keep buying after a price increase, either one by one or in bulk. First, we'll test a customer with low total spending, a low average order value, infrequent purchases, and a long time since their last booking. They're not a loyalty member, booked far in advance, and chose a domestic economy flight. The model predicts they're likely to stop buying, with a low probability of continuation. Next, we try a customer with high total spend, frequent purchases, and recent activity. This customer is a loyalty program member, booked close to the departure date, and chose an international business class ticket. The model predicts they're likely to continue buying, with a high probability of continuation. In the batch prediction section of the app, you can upload an Excel file containing customer features. Here I have a file with 50 customers. After uploading, we click on Predict, and the app returns the results. Batch prediction complete. You can then download the updated file, which now includes 2 new columns, prediction and probability for each customer. In the Visual Analytics section, you can upload these results to explore probability distributions and better understand overall customer sensitivity patterns. Price optimization needs to happen in real time, when a customer logs in, searches, or views a product page. So how does our model work behind the scenes in a booking platform? To simulate this behavior, we use a local stub backend, a mock server that mimics how the platform would interact with the model in production. When a customer logs in, acts their latest activity data, send it to our deployed prediction API. If the model predicts the customer is likely to continue buying after a price increase, it dynamically increases the price, let's say 10%, before showing the page.
Let's see how it works locally. I start the Flask app and trigger a booking simulation. The output shows the action taken, whether the price was increased or kept the same, along with the original price and the final price shown to the customer. You can run the simulation multiple times to see how pricing adjusts dynamically, based on different customer profiles. Let's see how to integrate our ML model into production software. This is how the model connects to a real booking platform. When a user searches for a flight, the backend collects their session data and sends it to our price sensitivity API. If the API predicts they'll tolerate a price increase, the system adds a markup, for example 10%. before showing the final price. The logic mimics what platforms like Expedia use to personalize pricing in real time. But what if the API is slow or fails? We include a fallback mechanism. If the response takes longer than 50 milliseconds, the system skips the markup and shows the base price instead. This ensures speed and reliability. Price sensitivity modeling is just one example of how data can drive better business outcomes. I'd be happy to discuss how it can be adapted to your platform.